Hello. When conducting inferential statistical analysis and trying to draw conclusions about a population based on a sample, we often wonder how to even start, if there are some steps that we may need to follow, and what to do with the results. Learning how to run the statistical analysis is only part of the process. Before we even begin working with data, we have to think about our study and take some preliminary steps. In this presentation, I will provide a conceptual overview of the hypothesis testing process. Specifically, I will explain and provide examples of null and alternative hypotheses. I will explain the distinction between one-sided and two-sided alternative hypotheses and when to use each one. I will explain the general steps involved in hypothesis testing and explain the notions of type 1 and type 2 error and the relationship between them in hypothesis testing. Hypothesis testing is a fundamental statistical method used to determine whether there is enough evidence in a sample of data to infer that a certain condition is true for the entire population. This process involves making an initial assumption, which is called a null hypothesis, collecting data, and then determining whether the evidence supports or contradicts the null hypothesis in the favor of an alternative hypothesis. The null hypothesis, noted HO or H0, is a statement of no effect or no difference or no relationship, which researchers aim to test against. For example, there is no difference in test scores between students who use a digital textbook and those who use printed textbooks. The alternative hypothesis, noted H1 or HA, is a statement that contradicts the null hypothesis, indicating some effect or some difference or some relationship. For instance, students who use digital textbooks have higher test scores than those who use printed textbooks. The null hypothesis serves as the default or a starting assumption in hypothesis testing. You may now wonder why hypothesis testing is done this way. Why do we need to start with a null hypothesis? This is because, statistically speaking, it is easier and more practical to prove that a statement is not true than to test all of the alternatives. By excluding the null hypothesis, a researcher can then assume that the opposite or all the alternatives of the null hypothesis must be true. Therefore, the null hypothesis is presumed true until the evidence indicates otherwise. For example, a researcher wants to test whether a new teaching method improves student test scores. The null hypothesis in this case might be the new teaching method has no effect on student test scores, which can be formally written as mu1 equal mu2 or mu1 minus mu2 equals 0, where mu1 and mu2 are the means of the test scores for the new and for the traditional teaching methods. The alternative hypothesis is a statement that contradicts the null hypothesis. It suggests that there is in fact an effect or a difference or a relationship. The alternative hypothesis is what the researcher suspects might be true based on prior knowledge or experience and wants to support through evidence gathered from the sample. It represents the researcher's actual expectation or belief. For instance, continuing with the same research scenario, the alternative hypothesis might be the new teaching method improves student test scores, which can be formally written as mu1 different than mu2, or mu1 is larger than mu2, where mu1 is the mean test score with the new teaching method and mu2 is the mean score with the traditional teaching method. There are two types of alternative hypothesis: directional or one-sided and non-directional or two-sided. A directional alternative hypothesis specifies the direction of the expected effect or difference. It states that one group or condition is expected to be greater or less than another. This type of hypothesis is used when there is a specific predicted direction of the relationship or difference. For instance, in an educational study, a researcher might hypothesize that students who participated in an after-school program will have higher test scores than those who did not. This can be formally written as mu1 is larger than mu2, or mu1 minus mu2 is larger than 0, where mu1 is the mean test score for students who attended the after-school program, and mu2 is the mean score of the students who did not. A non-directional alternative hypothesis does not specify the direction of the expected effect or difference. It simply states that there is a difference or effect, but does not predict whether it will be higher or lower. This type of hypothesis is used when the researcher wants to test for any difference regardless of direction. Using the same educational study, the hypothesis might be in this case there is a difference in test scores between students who participated in the after-school program and those who did not, without specifying whether one would be higher or lower. This can be formally written as mu1 is different than mu2, or mu1 minus mu2 is different than 0. You may wonder why we don't always use two-sided alternative hypotheses to cover both possibilities in one test. When conducting research, the choice between a one-sided or one-tailed hypothesis and a two-sided or two-tailed hypothesis depends on the objective of the study, the research question, and the expectations regarding the direction of the effect. In general, we should use a one-sided alternative hypothesis if the research question or theory predicts a specific direction of the effect. For instance, if previous studies or theoretical frameworks suggest that a new teaching strategy will improve student outcomes, the hypothesis can be stated in one direction. Moreover, one-sided tests have more statistical power than two-sided tests when the effect is in the predicted direction. This means that a one-sided test is more likely to detect a true effect when it exists because the critical region for the rejection of the null hypothesis is all in one tail of the distribution. Sometimes only effects in one direction are practically significant or relevant. For instance, a school might only be interested in whether a new program increases student performance. If there is no increase, then the result is sufficient to consider the program ineffective, and there's no need to allocate additional resources to continue the program. There is no need to test if there is a decrease because this will lead to the same decision. Another example are clinical trials or safety studies where researchers might be more interested in detecting adverse effects or benefits in one direction to make quick and ethically sound decisions. In contrast, if there is no strong theoretical or empirical basis for expecting the effect in a specific direction, a two-sided hypothesis is more appropriate. It tests for the possibility of an effect in both directions. Two-sided tests are more conservative, meaning that they reduce the risk of type 1 error, which means incorrectly rejecting the null hypothesis when it is in fact true. This is important in exploratory studies or when the consequences of a type 1 error are severe. Two-sided tests also provide more comprehensive analysis by allowing for the detection of any effect regardless of direction. This is crucial in the early stages of research or when effects in both directions are theoretically plausible. By carefully considering the research question, the theoretical expectations, and the practical implications of the results, researchers can make an informed choice between one-sided and two-sided hypotheses. Hypothesis testing is a systematic method used to make decisions about population parameters based on sample data. The first step in hypothesis testing is stating the null hypothesis and the alternative hypothesis, as we have just discussed, which are based on the research question. The second step is choosing a significance level, also referred to as alpha. The significance level is the probability of rejecting the null hypothesis when it is in fact true. This is called a type 1 error. Common choices for alpha are 0.05, 0.01, and sometimes 0.10. The choice of alpha level varies by field or by the type of study due to differences in the context, consequences of errors, standards of evidence, and the nature of the research being conducted. In medical research, for instance, the cost of a false positive might include unnecessary treatment or patient anxiety leading to a preference for a lower alpha level like 0.01. In contrast, exploratory fields like social sciences or educational research typically use a higher alpha level such as 0.05 to avoid missing potentially important findings or the type 2 error. The third step in hypothesis testing is calculating a test statistic. The choice of the test statistic depends on the type of data, the specific hypothesis being tested, and the specific analysis that are needed. Common test statistics include t-tests, used for instance for comparing two sample means, z-tests, which are used for comparing means but when the sample size is larger and has a normal distribution and the population variance is known. ANOVAs or F statistics when we're comparing the means from 3 or more groups. Chi-square tests, for instance, when we examine relationships between categorical variables, and so on. The actual calculation of the test statistic varies based on the type of statistical test that we are conducting, but the general steps of hypothesis testing are the same across all procedures. The last step is to decide whether to reject or accept the null hypothesis based on the value and the probability of the test statistic, which we usually obtain from statistical software. Specifically, if the sample test statistic exceeds a specific critical value or a cutoff value and has a probability lower than alpha, we reject the null hypothesis and we accept its alternative. If the test statistic does not exceed a cutoff value and has a probability higher than alpha, then we accept the null hypothesis and we reject the alternative. In hypothesis testing, type 1 and type 2 errors are two potential mistakes that can occur when making decisions about the validity of the hypothesis based on sample data. A type 1 error can occur when the null hypothesis is in fact true, but we incorrectly reject it. The probability of making a type 1 error is denoted by alpha, as we described earlier, which is also known as the significance level of the test. For instance, let's say that we use an intelligence test in psychological testing to detect a mental disability. A type 1 error would occur if the test indicated that a person had a mental disability when in fact she did not. A type 2 error occurs when the null hypothesis is false, but we fail to reject it. This means that we miss detecting an actual effect or difference. The probability of making a type 2 error is denoted by beta. Continuing with the intelligence test example, a type 2 error would occur if the test fails to detect the disability in a person who actually has it. Reducing the probability of one type of error typically increases the probability of the other. For instance, lowering alpha to reduce the chance of a type 1 error, making the test more stringent, can increase beta, leading to a higher chance of a type 2 error. Therefore, researchers must balance the risks of both errors depending on the context and the consequences of the decisions being made. In summary, type 1 and type 2 errors represent two kinds of mistakes in hypothesis testing, and understanding the distinction between them is crucial for interpreting test results and making informed decisions. In this presentation, I explained and provided examples of null and alternative hypotheses. I explained the distinction between one-sided and two-sided alternative hypotheses and when to use each one. I described the general steps involved in hypothesis testing and explained the concepts of type 1 and type 2 errors and the relationship between them. I hope that the explanations and the examples provided were helpful.